Have you ever just stopped and thought about how we can see something as tiny as a microbe and at the same time something as mind-blowingly massive as a galaxy? How is that even possible? Well, the answer to both lies in understanding one thing: light.
And that right there is what we're diving into, the science of ray optics. We're going to follow a single, humble ray of light on its journey, and you'll see how by learning to bend it and bounce it, we can literally unlock new realities. So here's the game plan. First up, we'll get to grips with what light actually is. Then, we'll get into its two main moves, bouncing and bending. From there, we'll check out the tools we've built to control it, and finally, we'll see how it all comes together to let us see the unseeable. All right, let's kick things off with the most basic question of all. Before we can start manipulating light, we kind of need to know, what is it anyway?
Okay, so this is the single most important idea for everything that follows. In the world of ray optics, we simplify things way down. We think of light as traveling in perfectly straight lines, and we call those lines rays. That's it. They're like the basic building blocks of everything we see.
And here are the basic rules of the road for light. It is incredibly fast, moving at 300 million meters per second in a vacuum. The colors we can see fit into a tiny window of wavelengths. But for our purposes, the big one, the golden rule, is that last one. Light always travels in a straight line, a ray, until something gets in its way.
So that leads to the obvious question, right? What happens when a ray of light does hit something? Well, that brings us to our first big concept, the art of the bounce, or, as the physicists call it, reflection. Now, this isn't random. Light follows two really simple rules. First, the angle it hits a surface at is the exact same angle it bounces off at. You can think of it just like a pool ball hitting the cushion. And second, the incoming ray, the bounced ray, and the surface normal are all on the same flat plane. Super simple, super predictable, and, as we'll see, super powerful.
And this is where we humans got really clever. By curving a surface, we can control how those rays bounce. A concave mirror, just think of it as carving inward like a cave, collects all the light rays and brings them together at one single point. A convex mirror does the opposite. It bulges out and scatters the light, making it look like it's spreading out from a point behind the mirror. So, how do we know exactly where that reflected image is going to show up? Is it just guesswork? Nope, not at all. There's this neat little bit of math called the mirror formula. It's basically a GPS for light. If you know where your object is and you know the curve of your mirror, you can calculate precisely where the image will pop up. It's the blueprint behind the magic. But bouncing isn't the only trick light has up its sleeve. Sometimes, instead of bouncing off something, it goes right through it. And when that happens, we get to see the science of the bend, or as it's officially known, refraction.
You've definitely seen this before. You know, when you put a straw in a glass of water and it looks kind of broken? That's refraction. When light moves from one substance, like air, into another, like water, it actually changes speed. And that change in speed makes it bend. The denser the new stuff is, the more it bends. And just like with reflection, this bending is anything but random. There's a rule book for it, and it's called Snell's law. It lets us predict the exact angle of the bend. All you need to know is the angle the light comes in at, and a special number for the material called its refractive index. With those two things, you can map out light's path perfectly.
Okay, now this is where things get really wild. Get this. If light is trying to go from a dense medium back into a less dense one, say from water back into air, and it hits the boundary at a really steep angle, a critical angle, it can't get out. It's trapped. Instead of bending, it reflects completely back into the water. We call this total internal reflection.
So why should you care about this weird light-trapping trick? Well, you know that sparkle in a diamond? That's just light getting trapped inside, bouncing around because of total internal reflection. And even crazier? The internet. The entire modern internet runs on light signals bouncing down hair-thin glass threads called optical fibres, all thanks to this one amazing principle.
So, we've got the bounce and we've got the bend. Now let's talk about the tools we've engineered to control that bend with absolute precision. I'm talking about lenses. Lenses are basically to refraction what mirrors are to reflection. A convex lens is thicker in the middle, and it brings light rays together, it converges them, just like a concave mirror. And a concave lens, which is thinner in the middle, does the opposite, spreading the light out. And you guessed it, just like with mirrors, there's a formula for that. The lens formula is the secret sauce that lets engineers design everything from the camera in your phone to giant telescopes. It tells them exactly where the image is going to form every single time. You know when you get a prescription for eyeglasses? That number they give you is the lens's power, and it's measured in something called diopters. It's really just a simple way of saying how strongly that lens can bend light. A higher number means a stronger bend. Convex lenses get a positive number, and concave lenses get a negative one. Okay, now for the grand finale. This is where we put it all together. We're going to see how we combine these simple principles of bouncing and bending to build instruments that basically give us superpowers. Let's start small, really small. Your basic magnifying glass? That's just one convex lens, simple. But to see the truly microscopic world, we need to level up. A compound microscope uses two lenses. The first one, called the objective, creates a magnified image. Then the second lens, the eyepiece, magnifies that image. It's a powerful 1-2 punch of magnification. Now let's flip it and look at things that are impossibly huge and far away. A telescope uses the exact same ideas as a microscope, but with the opposite goal. Instead of making something tiny look bigger, it makes something enormous and distant look closer. Its big main lens or mirror isn't for magnifying, it's for gathering as much faint light as it possibly can from a distant star. Then, an eyepiece takes all that collected light and magnifies it into an image you can see. So let's just recap the journey here. It all starts with one simple idea. Light travels in straight lines. We learned it follows two predictable rules. It bounces and it bends. We then figured out how to build mirrors and lenses to control those rules. And by combining them, we created amazing instruments that completely shattered the limits of what our eyes can do.
So, from the hidden world inside a single drop of water to the farthest galaxies in the cosmos, mastering light has let us see the universe. The only real question left is, with all this power in our hands, what are we going to look at next?